In this video, we're going to talk about the exponential form of the Fourier series. This is our overview slide, which we'll spend less than 5 minutes going over before we go over each of these topics in more detail and with more examples. The first thing we'll talk about is the exponential form of the Fourier series. So if we want to represent a function s of t, we can do that with the series from n equals negative infinity to infinity, c to the n, e to the I, omega n t. Omega n is our frequency, which is equal to 2 pi n over our period. C to the n, then, our coefficients for the nth frequency is 1 over t naught, integral from t naught to t naught plus t0, this t0 being our period, of f of t times e to the minus I omega n t. And actually this f of t, really I should have put s of t, so maybe I'll change it, or I'm going to change this one to f of t in a minute. Actually, I'll do that now. And to derive this formula, which we will do in this video, we essentially went back to our last video, took the formula for the Fourier series, and then for cosine, we substitute this Taylor series expansion that we had done like several videos ago when we were talking about Taylor series. Cosine is equal to 1/2 e to the I theta plus e to the minus I theta, and sine is equal to 1 over 2i e to the I theta minus e to the minus I theta. And then its orthogonality conditions for exponential terms finalizes our form to, for Cn that we see here. Next, we'll go over properties of the exponential series that can simplify calculations. The first fact is that C naught is equal to the average of f of t over the period. The second fact is that if f of t is a real function, if it's purely real, then f of t is equal to the complex conjugate of f of t. That's this asterisk sign, the complex conjugate, because, well, the imaginary part is 0 if it's purely real. And the exponential Fourier series coefficients will have conjugate symmetry. In other words, C of n, the nth coefficient, will be equal to the complex conjugate of C of n. The converse of this statement is also true. That is, if the exponential Fourier series coefficients are conjugate symmetric, then f of t is a real function. And one other note, if f of t is real, then the magnitude of Cn is even, and the phase or the angle of Cn is odd. The last property is one I had alluded to in my last video. If f of t is a real even function of t, then the coefficients of its exponential Fourier series are all purely real, and the series will contain only cosine terms. It kind of makes sense. If you have an even function, you're going to model it with cosines because the cosines are even functions. It would be really hard to get an odd function to look right when you're modeling an even function. Second, if f of t is a real odd function, then the coefficient complex conjugate is equal to the negative coefficient, and the coefficients are purely imaginary. And the exponential Fourier series will contain only sine terms. So again, you would model an odd function with sine because sine is an odd function. So if f of t possesses neither odd nor even symmetry, then the coefficients of the exponential series are complex, and the sine-cosine series is made up of both sine and cosine functions. And this last point we're not going to really go into in this video, but I should state it that the convenience of the exponential form, a major advantage of the exponential form of the Fourier series becomes evident when it is used with differential equations. That's it for the overview, so we'll go back and we'll start by deriving the exponential form of the Fourier series. To derive this formula here for the exponents of our exponential form of the Fourier series, which is equal to f of t, is equal to the summation from n equals negative infinity to infinity, c of n, e to the I omega n of t, where c of n is equal to 1 over t naught, that's our period, integral t0 to t0 plus our period, f of t e to the minus I omega n t. To get the formula for this coefficient, we start off with our trigonometric definition, our sine and cosine definition of the Fourier series from our last video. So we said that f of t is equal to a naught over 2 plus the sum from n equals 1 to infinity a n cosine omega n t plus the summation from n equals 1 to infinity bn sine of omega n t. So this is the form of the Fourier series that we had looked at in the previous video. Now we can substitute for cosine and sine this formula here for cosine and sine that we got when we were expanding cosine and sine using the Taylor series expansion. So this, we had worked out the formula for this in our previous video on Taylor series. So we said cosine of theta is equal to 1/2 times e to the I theta plus e to the minus I theta, and sine of theta is equal to 1/2 I, so the i's underneath also as part of the denominator, e to the I theta minus e to the minus I theta. So substituting that in here, we have am cosine omega mt plus bm sine omega t is equal to am over 2, the 1/2 comes from here. The cosine is going to get e to the I omega mt plus e to the minus I omega mt plus, now we have the bm, this 1/2 over I gives us a 1/2 over I here, and then e to the I omega mt minus e to the minus I omega mt. Grouping according to our exponent, so my e to the I omega t, where this is positive, I can group my am over 2 and my bm over 2i. So this is going to be my coefficient if n is greater than 0. And then over here, we have our e to the minus I omega nt. So we're going to have our am over 2 minus, now, because of this minus sign here, bm over 2i. So this is our Cn if n is less than 0. So this here is going to give us that our coefficient is equal to a naught over 2 if n is equal to 0, an minus I bn over 2 if n is greater than 0, this formula here, and an plus I bn over 2 if n is less than 0, which is this formula here. What we have shown is we can calculate Cn, and they are related to our an and bn that we had from our previous video, but really it's not like we're going to calculate all the a and bn and then change to the form of Cn. It's the orthogonality conditions of the sines and cosines, which we showed in our last video, that's going to let us finalize our formulas for Cn. So I'm not going to go through the derivation of this final form, but this is the formula that we're going to use to do the exponential Fourier series. So f of t is equal to the sum of n equals negative infinity to infinity Cn e to the I omega nt, where Cn is 1 over the period, integral from t naught to t naught plus the period, f of t e to the I omega nt. And this is the formula that I will leave up here for your reference. The next thing we'll look at are the properties of the exponential series. The first property is the C naught term, which can be given by the formula 1 over the period, integral from 0 to the period f of t, is equal to, this bracket is the notation for the average of f of t over our period t naught. The second point is if f of t is a real function, that means the imaginary portion, the part that gets multiplied by I, is equal to 0, then f of t is equal to the complex conjugate of f of t, and that's because the imaginary part is equal to 0. So when you take the complex conjugate, it's still equal to the original function, and the exponential Fourier series coefficients will be conjugate symmetric. That is, also our coefficients is equal to the complex conjugate. So the converse of this last statement, that is, if we say the exponential Fourier series coefficients are conjugate symmetric, that is Cn is equal to the complex conjugate of Cn, then f of t is a real function. So that's rewritten here. This last property, I kind of cleared out some space to make some room so I could put this graph here. So if f of t is a real even function of t, then the coefficients of its exponential Fourier series are all purely real. In particular, the series will contain only cosine terms. And that sort of makes sense. If you want to model an even function, you're going to use cosine because cosine is an even function. If you look at this, if you have something that's symmetric about the x-axis, it makes sense you're going to use a bunch of cosines, other things that are symmetric. It's going to be really hard to get that symmetry if you're starting with this odd function. Similarly, if f of t is a real odd function, then our complex conjugate of our coefficient is equal to negative coefficient. The coefficients are purely imaginary, and the exponential Fourier series then will contain only sine terms. So again, if you're going to model an odd function, you're better off starting with an odd function, which is sine. So if f of t possesses neither odd nor even symmetry, then the coefficients of the exponential series are complex, and the sine-cosine series is made up of both sine and cosine functions. I'm going to state these properties without proof, and I'm also going to state this last point, that a major advantage of the exponential form of the Fourier series becomes evident when it is used with differential equations, also without an example of this last one. And I'm going to skip this type of derivation in favor of doing two examples of finding the Fourier coefficient when we're doing a Fourier expansion of a function. Our first example is this rectified sine wave. So f of t is equal to sine of t for t between 0 and pi. You can see here then our period is equal to pi. Sorry, this should be equal to pi. And that makes our frequency, which I have this formula here from our last video, frequency of n is equal to 2 pi n over our period, which is pi, so this is going to give us 2n. Using our formula for Cn, it's equal to 1 over t naught, our period, which is pi, 0 to pi, that's from t naught to t naught plus our period. Then we need our f of t, which is sine of t, e to the minus I omega n t. Now, substituting, I want to substitute this sine into exponential form so I can work with it with my other exponential form. So my sine of t is going to be 1 over 2i e to the it minus e to the minus it, and then I have that times e to the minus I omega n dt. Here all I did was I pulled out my 2i outside my integral, and then the next thing I'm going to do is multiply my exponent here, my e to the minus I omega n t times e to the it, and then times e to the minus it. So I'm going to get e to the it times 1, and then over here minus omega n. Then I have my minus sign, e to the it again times, oh, I put a minus outside, so e to the minus it times 1 plus omega n. When I integrate each of these exponents, all I need to do is take the thing that multiplies t and put it in the denominator. So I have my 1 over 2 pi I, e to the minus, or e to the it times 1 minus omega n divided by, now just whatever is multiplied by t, my I, 1 minus omega n. And I'm going to evaluate that between 0 and pi. Similarly, over here, when I integrate, I'm going to get my e to the minus it over 1 minus omega n, and then I do have this minus sign, but I went ahead and combined it with this minus sign because I have to divide by negative I 1 plus omega n, and the negative I over here comes over here to make that a positive, and I evaluate that between 0 and pi. Over here I plug in my pi, and then later I plug in my 0, so this becomes a 1. Similarly, over here, I plug in my pi and I get this term. I plug in my 0 and I have this term here. I'm not sure why I waited so long, but I decided I needed to convert my Wn, which I have is equal to 2n. So I'm going to plug in 2n for my Wn. That'll help me look at this exponent better. The reason why this is going to help us by putting the 2n is we can look at this e to the I pi. This here we're on the unit circle because the radius is equal to 1. There's a 1 in front of the e I pi. And then the radians, the number of radians we go around in the counterclockwise direction is pi. So we're here, we're at radius 1. We go counterclockwise pi radians, which puts us at -1. So e to the I pi is equal to -1. Now this 2n times I pi, it's in the negative direction. If we go around twice pi, we're going to end up back where we started, whether we go counterclockwise or clockwise. So essentially this here is going to be equal to -1. Similarly, over here, our negative e to the minus I pi times 1. The radius is 1, so we're on the unit circle, and we're going negative pi radians in the opposite direction, so that's in the clockwise direction. That puts us at -1. And now if we multiply 2n times I pi, again, we can go around again 2 pi times as many times as you want, as many n times that you want. We're going to end up back at -1. So this here and this term here, both of these numerators are equal to -1. This -1 combined with this -1 gives us -2, and similarly, this -1 combined with this -1 gives us -2. A little more algebra, and we can get an even simpler form, 2 over pi times 1 minus 4 pi n squared. And that's the solution for our nth coefficient of our Fourier series. Our next example is this sawtooth wave. Our function is equal to a naught, that's our amplitude, over 2 pi times t, where t goes between 0 and 2 pi. So our period is 2 pi, and our omega n, which is 2 pi n over period, so our omega n is going to equal to n. Using our formula for Cn over here, Cn is equal to 1 over our period, which is 2 pi, integrating from 0 to 2 pi, integrating over 1 period, dt, of our function f of t, which is a naught over 2 pi t times e to the minus I omega n t. The first thing I'm going to do is pull out this constant a naught over, why do I have this? Oh, this 2 pi times this is 4, and this pi times this pi is pi squared. Our integral from 0 to 2 pi, t times e to the minus I omega n t. Here we're going to integrate this using integration by parts. So our exponential form does not save us from integration by parts. So we're integrating u v prime dx is equal to uv minus integral v u prime dx. And we're going to choose u is equal to t so that u prime is equal to 1. So again, we want to choose u so that when we take u prime, it simplifies. If we had chosen e to the minus I omega n t as u, when we took u prime, we would still have something just as complicated. In fact, we would have minus I omega n e to the I omega n t, which is, a tiny bit more complicated. But anyway, we chose v then to be e to the minus I omega n t. That's v prime, sorry. That means v, when we integrate it, is minus 1 over I omega n e to the minus I omega n t. So plugging into our formula, u times v, that's t times this v here. So t over minus I omega n e to the minus I omega n t, evaluated 0 to 2 pi, times the integral of v times u prime. So u prime is 1, so we just need this v over here. I factored out my coefficient, and this -1 cancels with this -1 to give me a positive 1. 1 over I omega n, 0 to 2 pi, e to the minus I omega n t dt. I left this part unchanged so I can plug everything in all at once for the dramatic reveal. Here I integrated, so I have my I omega n squared, and because of this negative, this now becomes negative, and I have e to the minus I omega n t evaluated at 0 to pi, 2 pi, 0 to 2 pi. Plugging in my 2 pi first, so I have a 2 pi over minus I, and for whatever reason, this is when I decide to plug in n for Wn. E to the minus in, my t is 2 pi, minus, and when I plug in for 0, I'm going to get 0 because of this t term here. Similarly, for this term, I plug in my 2 pi, and I get over here my I over n squared. This I becomes -1, so I get a positive over 1 over n squared. I get e to the minus I n 2 pi, and when I plug in 0 over here, I get a 1 times my 1 over n squared. And just like our other example, we want to evaluate our e to the minus I n 2 pi, which this n just means it's a integer multiple of minus e to the minus I 2 pi. So e to the minus I 2 pi, let's look at that first. So the minus means we're going in the clockwise direction. 2 pi means we go around pi radians, which puts us right back at 1. We can do this n times. As many times as you want to do 2 pi, you're going to end up back at 1. So this becomes 1 here, and this also becomes 1 here. Here we're going to have 2 pi over minus in. Over here we're going to have 1 over n squared, 1 minus 1, which gives us at the end ai over 2 pi n. To review what we've done in this video, we looked at the exponential form of the Fourier series. So we can model any f of t as a series of n equals -infinity to infinity, coefficient cn times e to the I wn of t, where cn, the coefficient for the nth term, is 1 over t naught, where t naught is the period. Integral from t naught to t naught plus our period f of t times e to the minus I omega n t. Omega n being our frequency, which is 2 pi n over t naught. And we got this formula by taking our Fourier series that we did in the last video, which was trigonometric. In other words, it had sines and cosines. And we replaced our sines and cosines with the Taylor series expansion that puts cosine in exponential form, 1/2 e to the I theta plus e to the minus I theta, and sine in exponential form as 1 over 2i times e to the I theta minus e to the minus I theta. And then additionally, orthogonality conditions for the exponential terms finalized our formula for c of n here. And we did 2 examples, the rectified sine wave as well as the sawtooth wave, of how to find these coefficients. And I gave you, without proof, these properties of the exponential series that can simplify calculations. First, your c naught is equal to the average value of f of t over the period. Second, if f of t is a real function, that it's purely real, the sine part is 0, then our function is equal to the complex conjugate of the function, and the exponential Fourier series coefficients will also be conjugate symmetric. That is, our coefficient is going to be equal to the complex conjugate of the coefficient. The converse of the statement is also true. That is, if the exponential Fourier series coefficients are conjugate symmetric, then f of t is a real function. And I think I wrote this out here. The third property, that is, if f of t is a real even function of t, then the coefficients of its exponential Fourier series are all purely real, and the series will contain only cosine functions. So in other words, to build up this even function, we use cosine, which is also an even function. It wouldn't make sense to start throwing in some odd sine function terms. Also, if f of t is a real odd function, then the coefficients are purely imaginary, and the exponential Fourier series will only contain sine terms. Again, if you're building an odd function, you're going to use sine terms because they're odd. If f of t possesses neither odd nor even symmetry, then the coefficients of the exponential series are complex, and the sine-cosine series is made up of both sine and cosine functions. This last statement I did not give you an example of, just because I feel like it's beyond the scope of this video to start talking about differential equations, but a major advantage of the exponential form of the Fourier series becomes evident when it is used with differential equations. You might remember in your differential equations class that so many solutions were the form e to the RT. So this kind of falls right in with that. Okay, well that concludes this video. Thank you for watching.